Welcome back to Chem 4300. In this video, we're going to continue Chapter 17 on quantum mechanics of rotational motion. And now we're going to look at solutions to the Schrodinger equation for describing the rotational motion of symmetric molecules. And so here are a few sort of graphics giving you some examples of molecules that have the symmetry that are associated with symmetric molecules. Now, in the prolate symmetric case, we saw that there was the unique axis A, which had a principal component for the moment of inertia that was smaller than the other two, B and C. And so we're going to define that unique axis A as I parallel, and for B and C we call that I perpendicular. So when I write down the Hamiltonian that we did in the most generic way at the beginning, if we use this substitution up here, we get the Hamiltonian in this form here. So you can look at this and put them into here, and you can see that that will simplify to this term here. Now, remembering that J squared is equal to JA squared plus JB squared plus JC squared, I can do a little rearranging, and you can check this quickly at home, and I can turn this Hamiltonian into this form of the Hamiltonian, where now I have written it in terms of J squared and one component of the angular momentum vector. So in this form, I know that J squared and JA commute with each other. So what we know is that the Wigner-D functions that we solved for the spherically symmetric case, these are also the eigenfunctions for J squared and JA. So that will be the solution to the Schrodinger equation when we substitute in this Hamiltonian into H psi equals E psi. So the prolate and spherically symmetric molecules have the same eigenstates. That's these Wigner-D functions. Now, in this problem then, we're going to have the quantum number associated with JA, and that's going to be Kj, and this is going to be associated with rotation about the A axis of the molecule fixed frame, the body fixed frame. So Kj times h bar will be the projection of the angular momentum vector onto the A axis of the molecule. When that molecule is in a state with Kj equal to the maximum magnitude, so Kj equal plus J or minus J, then that prolate molecule is one that is rotating nearly parallel to the A axis of the molecule. When the Kj value has lower magnitude, say it's close to 0 or 0, then it's going to be rotating primarily around the B or the C axes. If I look at the energy expression I get now with using the eigenvalues for J squared and JA squared, this is what I get for the energy expression. And you can see it now depends on Kj, excuse me, unlike the spherically symmetric case. And when I write it in terms of the wave number representation here, so I have this energy in terms of wave numbers, it looks like this, where this A and B are the rotational constants, the wave number rotational constants. Excuse me. So one thing you'll notice is that there's no dependence on m sub j, and that's because the energy should be independent of the space-fixed frame. So no matter how the molecule is rotating, in the space-fixed frame, the projection onto the z-axis of the space-fixed frame should not be, the energy shouldn't be a function of how it projects onto the z-axis of the space-fixed frame, because it's only in the molecule-fixed frame that we will have some kind of dependence on the one component. So we'll see then that in all of our energy expressions that there'll be no dependence on m sub j because of the isotropic space that we're tumbling in. So now we will look at the energy levels written in terms of these wave numbers, where it's given by this expression here. And this Kj is the term that will now be different than what we had in the spherically symmetric case. This will shift the levels as Kj changes. So for j equals 0, 1, 2, 3, we see that there is the increase in the energy levels, and the gap between them is increasing as j increases, just like we saw in the spherically symmetric case. But we also see that as Kj increases, there's an increase in the energy with increasing magnitude of Kj. So here we see that Kj of plus or minus 1 is slightly higher than Kj of 0 for j equals 1, and then so on here. So like Kj for j equals 3, that you go from Kj of 0, Kj of plus or minus 1, Kj of plus or minus 2, or Kj of plus or minus 3. It continues to increase. And so it doesn't depend on the sign of Kj because Kj shows up squared in our energy expression. Now, this term, A minus B, is always positive for a prolate symmetric molecule. So for a prolate symmetric molecule, the increase with changing Kj squared is always going to be, it's always going to be a positive increase. So it will always go up as Kj increases in magnitude for a prolate symmetric molecule because this difference is always positive. Now, the energy level degeneracies for the Kj equals 0, they're all going to be 2j plus 1 fold degenerate. And that's because for Kj equals 0, there are 3 possible m sub j values. So we'll have, depending on the j value. So for j equals 0, well, there's only one value for m sub j. So this one will have just m sub j of 0 and Kj of 0. So that one will be singly degenerate. But for j equals 1, compared to j equals 0, j equals 1 with kj equals 0, we'll have 3 possible values for m sub j of minus 1, 0, and plus 1. So this one will be 3-fold degenerate, whereas kj of plus or minus 1 will be doubly degenerate due to the kj dependence here, and then additionally have the mj degeneracy. So whenever you have kj not equal to 0, then you'll have 2 times 2j plus 1 fold degeneracy. Okay, so just try to work that out for yourself there, but you know that as j increases, you're going to get a 2j plus 1 degeneracy for the m sub j part, and then with the k sub j in the prolate symmetric case, then you'll get an additional double degeneracy, a multifactor of 2 for the kj's that are non-zero because this term shows up squared. Okay, in the oblate symmetric molecule, we have our unique axis as C, and A and B are equal to each other. So we'll write down I parallel is equal to C and I perpendicular is equal to A and B. So then when we write it down our Hamiltonian, making this substitution up here, we can do a little rearranging like we did in the prolate symmetric case, and we can write it in terms of the angular momentum vector squared and one component, in this case, JC. And so we know that the angular momentum squared in one component will commute, so we can get the eigenstates of this Hamiltonian as long as they're, because these guys commute, it will be the eigenstates of J squared and JC, which have the same eigenstates. So we know that the Wigner-D functions are the eigenfunctions for this Hamiltonian. So oblate and prolate and spherically symmetric eigenstates have the same form. It's these Wigner-D functions. Now, in this case, the Kj quantum number is associated with rotation about the unique axis, which is C in the oblate case. In the prolate case, it was A, and in the oblate case, it's going to be C. And so the Kj times the h bar is going to be the angular momentum that is the projection of J onto the C axis of the molecule fixed frame. When Kj is equal to plus J or minus J, so when it has its maximum magnitude of value, then in the oblate case, that means the molecule will be spinning nearly parallel to the C axis, whereas when Kj is very small or close to 0, then in the oblate case, it's going to be spinning about A or B primarily. All right, now we come to the energies, and again, taking the eigenvalues, we get this expression in terms of wave numbers, and these constants B and C are those rotational constants. This is the wave number rotational constants. And once again, there is no dependence on mj because of the isotropy of space. So we will have a degeneracy associated with all the j values that have mj values from minus j to plus j. And when we look at the energy level spacing, energy level diagrams here, we see, I'm going to write this differently here. So now I'm going to put the kj equals 0 and increase kj going to the left, the opposite of what I did for the Prolate case. And here we see j equals 0, 1, 2, 3, and so on. We see the increasing gap as we increase j. But now we see that, like the Prolate case, that there is a 2j plus 1 degeneracy associated with the kj of 0. So, well, of course, j equals 0 is singly degenerate, but then j equals 1, threefold degenerate, and then j equals 2 is fivefold degenerate for all of these kj equals 0 states. But when we get to the kj not equal to 0 states, so then we get an additional factor multiplier of 2 because we have plus or minus values are degenerate, so we get 2 times 2j plus 1. Now, in the oblate case, this difference, c minus b, is always negative. And that means that when we increase kj, the levels will always go down. And that's the opposite of what we found in the Prolate case, where they always went up. So when we look at these diagrams, when you see the energy levels going down, you know you're looking at the oblate case. This difference here should always be negative. So when you bring them together then, the oblate case here on the left, the Prolate case here on the right, I've grouped the kj's equal to 0 next to each other, and you can see that those are going to look pretty exactly the same. But then as you increase kj in magnitude, in the Prolate case, each one of those j levels will move up with the kj changing, increasing in magnitude. Whereas in the oblate case, as you increase the magnitude of kj, then each of those j levels will start to decrease. Okay. The last example I'll do in this video is the asymmetric molecule. Just some random example here, caffeine. And this is the case where we can't do any kind of rearranging to put it in terms of the total j squared and one of the components. So we're stuck with this Hamiltonian, and this Hamiltonian is not an eigenstate of j squared in one of the angular momentum vector components. So we have a problem where we're not going to be able to find a solution as simply as we did before, even though we just looked up the solution. So in this case, though, we do know that if there's no torque being applied to our molecule, we know that angular momentum should be conserved, and so that means that the total j will be conserved in this case, regardless of whether it's asymmetric or not, and j and mj will still be good quantum numbers. But because of this not being an eigenstate of j squared or one of the components, the projection of j on any of the molecule fixed axes is not going to be constant, so kj will not be a good quantum number in the asymmetric molecule rotational motion case. Now, this is where you really have to either apply numerical methods or some kind of perturbation approach. If you're lucky, you can do a perturbation approach. If you're not so lucky, you have to go to do a full numerical evaluation of this problem. But if you were going to do a perturbation approach, one way you could do it is you could think about the asymmetric molecule as deviating from some symmetry where you already know the answer to. So take a perturbation approach where you have an H naught, where you know the solution, and look at a perturbation that causes you to deviate from the known solution. So here we could write down this Hamiltonian with a little bit of algebra. You can put it in this form, where on this side we have something that looks exactly like the Prolate symmetric, although with a little bit of modifications here. It has sort of the form of a Prolate symmetric Hamiltonian, where we have j squared and ja, and we know the solutions for that form. And this part here can become a perturbation if it's not big compared to these terms. So that could happen if it's very close to Prolate symmetry. You could solve the problem with this form. Similarly, you could do the same thing with it if it was closer to oblate, but deviating slightly from oblate. you can rearrange this in terms of j squared and jc squared and write some term over here where it's treated as a perturbation. But if it's somewhere in between those two extremes, then you have a situation where you have to just fully numerically diagonalize this. But it will turn out, though, that you can write whatever the solution you get for this, it can be written as a linear combination of those Wigner d rotation functions. Okay, so we'll end this video here, and in the next video we'll look at the solutions for the linear molecule.